So the next thing is we were discussing about the you can say the driven motion, the spring mass system driven motion, where some force is applied to a system. We solved this example here. Now I am going to further explain this example. So here I am using two terms, that is transient and the steady state terms. When f is periodic function, you can say that there is some cycle over the time, such as f of t, which is equals to in the form of f naught sine, you can say lambda t, plus, or f of t which is equals to cos lambda of t, omega t. The general solution of 25 for lambda greater than 0 is the sum of the non-periodic function xc of t, complementary you can say solution, and the periodic function. Moreover, x of t dies off as the time increases, that is limit t approaches to infinity, xc of t equals to 0. You can say when the time approaches to infinity, then the complementary solution approaches to 0. Thus, for a long period of time, the displacement of the mass are closely approximated by the particular solution. The complementary function is said to be the transient term or the transient solution, and the function xp of t, the part of the solution that remain after an interval of time, is known as the steady state term or the steady state solution. It means that the solution which fades off, or you can say the solution which over the time that is equals to 0, that solution, that complementary solution, is known as the transient term, and the other solution which remains still, or you can say which remain for the long time, for the interval of the time, then that function is basically known as the steady state term. Note therefore that the effect of the initial condition on the spring mass system driven by the f is transient. In the particular solution 28, now they are discussing this equation of the motion, where e minus 3t 38 over 51 cos of t minus 86 over 51 sin t is transient term, and xp of t, which is equals to minus 25 over 102 cos 4t plus 50 over 51 sin 40 is steady state term. This means that this term goes to 0 after some time, but this remains steady. The graph of these two terms and the solution of the 28 are given in the figure, you can say here. So this is the transient and this is the steady state. So this is the constant term, but these transient, you can say as over the time this is equals to 0, but this function remains same. This is same over some, you can say over some long period of time, but that function, that the transient term, that function approaches to 0 over some time. So this is the, you can say, transient and the steady state term. Further, they are explaining, they are taking another example here. This is some initial value problem. This is the initial condition given here. They solve this question and find that solution. Here in that term, this is the transient, you can say the state, and this is the steady state. Further is we have the differential equation of the driven motion without the damping. So here is the example. I am going to explain this with some example here. This is the question given here. This is the initial condition where f naught is constant and lambda is not equals to omega. Gamma is not equals to omega. So the complementary function of this equation is this one, and to obtain the particular solution we assume xp of t, which is equals to a cos gamma t plus b sin gamma t. So that in that case, now I am converting this, you can say, equation into the form of xp. So x double dash of p plus omega square xp, which is equals to f naught sin gamma t. Now putting the value of x double dash of p into that equation and x of p into that equation, I got that result. So this result is equals to f naught sin gamma t. Now comparing both sides, I got that result, that is a equals to 0 and b, which is equals to f naught over omega square minus gamma square. So therefore xp of t is equals to, now putting the value of a and b here in that you can say in that particular solution I got that result. That is the, you can say, the particular solution. Applying the given initial condition to the journal solution. Now I am going to apply this initial condition, that is x of 0 equals to 0 and x dash of 0 which is equals to 0, and this condition I got that result, that is x of t which is equals to, putting the initial condition here and also here, I got this result, that is c1 cos omega t plus c2. In that, you can say, in that equation, when I put this initial condition x of 0 equals to 0, I got the value of the c1 and the value of the c2 by putting this initial condition. So putting the values of the c1 and c2 in this equation, I got that result. So this is the you can say undamped force motion